In this video, we will look into the basics of an inductor. We will see how a magnetic field is induced, the EMF generated, and the current voltage relationship of an inductor. So let's look into the basic feature of an inductor. An inductor is a passive element which stores energy in terms of magnetic field. A passive element is an element which absorbs power and either stores it or converts into heat. It opposes the sudden change of current in the circuit. To understand the working of an inductor, let's first look into some basic concepts. When current passes through a conductor, magnetic field develops around the conductor. Here is a conductor and current is passing through it and magnetic field develops around it. Now, if we increase the current, the magnetic field gets stronger. So, we can say that the magnetic field developed is directly proportional to the magnitude of current passing through the conductor. The direction can be determined using Maxwell's right-hand rule, or also referred as corkscrew rule. Now we see the current flowing in the conductor upwards. We point the thumb in the direction of the current flow and wrap the conductor with the fingers. The curling of the fingers around the conductor indicates the direction of magnetic field. Here, the direction of magnetic field is anti-clockwise. We can see the case for the current flowing downwards as well, which will be in clockwise direction. Now we know that the current flow results in the development of magnetic field around a conductor. So when a straight wire is shaped into a coil and current passes through it, magnetic field develops in such a way that it gets concentrated around the coil. This makes the field stronger. Let's take a section of the coil and see how the field lines are being arranged. The current flow results in generation of magnetic field lines and the direction is according to the corkscrew rule. We see that the direction of the field lines on the inside of the coil is downwards while on the outside it's upwards. The flux lines all add up and we obtain the flux lines moving from inside to outside. Now if we look into the coil, we see the field lines are passing from one side to another in a way similar to a magnet with the lines moving from north to south. The coil resembles a bar magnet and the magnetic property developed is due to the current flow in the coil. So it is referred as an electromagnet. Another way of finding the magnetic north is by curling the fingers in the direction of the current flow in a coil. Here, we wrap the coil with the fingers in a direction similar to the current flow, which in this case is towards us. The thumb then points to the direction of the magnetic north. Same process is applied for current flowing in opposite direction. Now, as the current varies, the magnetic flux lines also varies around the coil. When there is a change of flux in the area enclosed by the coil, EMF is induced. And this is according to the Faraday's law of electromagnetic induction. According to this law, the EMF induced in a coil is directly proportional to the rate of change of flux enclosed by the coil and the number of turns in the coil. We get an expression like this. The negative sign is to show the direction of the induced EMF. This is according to the Lenz's law. In simple terms, the law states that the direction of EMF induced is always opposite to the very cause of it. Point to remember, for EMF induction, there needs to be a varying magnetic field, which is possible when there is varying current flowing. So the current can be an AC supply or a DC supply with a switch. So according to Lenz's law, the direction of the induced EMF will be opposite to the direction of current. And we have the positive sign as such that the current from the coil opposes the current incoming to the coil. Now, as current in the circuit increases, the EMF opposes the increase due to the induced current in opposite direction. And when the current decreases, the EMF tries to maintain the current by releasing its stored energy. This feature to oppose the change in current is known as inductance. The EMF generated is referred as self-induced EMF since the magnetic flux generated is due to the coil itself. This EMF is directly proportional to the rate of change of current in the coil. Now let's look into the current and voltage relation in an inductor. We have the equation, and this can also be written as, now if we suppose the value of voltage as Vm sin omega t and use the integral equation to find the expression of current, we get a solution like this. Now using the expression for voltage and current, we plot the graph and we find something like this. Now if we see the starting point of two waveforms, the current waveform starts after an interval of pi by 2 than the voltage waveform. This results in a difference of pi by 2 between the two quantities. As the current completes its full cycle after the voltage waveform, we can say that the current waveform is lagging the voltage waveform by an angle of pi by 2. Here's a quick review of the concepts covered. When current passes through a conductor, magnetic field develops around the conductor. The magnetic field developed is directly proportional to the magnitude of current passing through the conductor. When there is a change of flux in the area enclosed by the coil, EMF is induced. The induced EMF in a coil will oppose the very cause of EMF induced. I hope you now have a better understanding of inductors and the stuffs behind its working. Please like, share and subscribe, and I'll see you in the next video.